In this second video about acids and bases, we need to discuss autoionization and also pH. pH is more a matter of definition. It's just a different way of expressing the concentration of H3O+. Autoionization, however, is more of a conceptual change. It really gets to the heart of what's going on in acid-base solutions in water. So this is the equation for autoionization. It turns out that in a water solution, even pure water that's not acidic or basic, every once in a while a water molecule passes a proton to another water molecule, and as a result you get H3O plus and OH minus. Okay, this is always happening, admittedly to a very small extent, but this is always present in any aqueous solution. So the equation reads 2H2O liquid forming an H3O plus and OH minus. And that's an equilibrium. It can go back the other way, and we can write an equilibrium constant for it. Here's the equilibrium constant. It's called Kw. Now it's again a Kc really. It's a molarity, molar concentrations that are expressed in this constant, in this expression. However, we give it a special name, Kw, and notice that water is left out. So it's products over reactants, and the products are H3O plus and OH minus. The reactants are just the water, liquid, and the concentration of the water isn't going to change in the course of this. It's a very, very slight amount that this occurs, so the concentration of water is left out of the expression. Okay, and the product of the two, H3O plus times OH minus, that has the value 10 to the minus 14 at 25 degrees. That can change. It can be different at a different temperature, but usually we're using this value 10 to the minus 14 for 25 degrees C. Okay, so this means that it's a little different way of thinking about the solution. One thing is, in any aqueous solution, both H3O plus and OH minus are present. This is in any aqueous solution. You might have in the past thought about acid solutions as having only H3O plus and no OH minus, base solutions having only OH minus and no H3O plus. Now, that's not exactly true. What really matters is the relative amounts. In an acid solution, you have much more H3O plus and probably a very tiny amount of OH minus. In a base solution, it's vice versa. But they're actually both present in all aqueous solutions, and their concentrations always multiply out to Kw. Okay, and that can be a wide range of things, right? Any aqueous solution. That can be a cup of coffee, that can be the ocean, that can be your blood, whenever it's an aqueous solution. So it's a wide-ranging applicability. Neutral means that the two concentrations are equal. Not that one or that they're both missing, but they're both present, but they're just equal. The H3O plus and OH minus. And if you think about it, if they have to multiply out to 10 to the minus 14 and they're both equal, that must mean that each one is 10 to the minus 7 molar. Okay. Acidic then just means that H3O plus is greater than 10 to the minus 7, while OH minus is less, right? So what happens if you went from a neutral solution to an acidic solution, H3O plus gets bigger and OH minus gets smaller. Okay, and they still multiply out to Kw. For basic solution, it's vice versa. The H3O plus is less than 10 to the minus 7, OH minus is greater than 10 to the minus 7. They still multiply out to Kw. Okay. So here's just an example. Anytime you have H3O plus, the concentration of H3O plus, you can figure out OH minus, and vice versa, because you know this relationship Kw equals H3O plus times OH minus. So here it's an acetic acid solution. H3O plus is 1.3 times 10 to the minus 3 molar. You simply say, okay, well then OH minus must be Kw over H3O plus, dividing both sides of the equilibrium expression by H3O plus. You arrive at that. And you plug in your values. 10 to the minus 14 divided by 1.3 times 10 to the minus 3 gives you 7.7 times 10 to the minus 12. So very, 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 very small, right? 10 to the minus 12, that's very small. But it's not zero. So this is a mildly acidic solution, 0.1 molar acetic acid, 1 times 10 to the minus 3 molar acid, something times 10 to the minus 12, actually I guess closer to 10 to the minus 11 molar in the OH minus, but both still present. But the point is, anytime you've got one of those, take 10 to the minus 14 and divide it by the one you got, and you get the other one, right? So OH minus is Kw over H3O plus. H3O plus is Kw over OH minus. Here then is the definition of pH. It's the negative base 10 logarithm of the H3O plus ion concentration. Okay. Notice I have off to the side here the log, or the base 10 log of 10 to the x is just x, right? You have to remember that. Okay. So if you look at this first entry in this table, I've got a bunch of examples here. Look at the first entry. 10 to the minus 7 molar H3O plus. Well, that is a neutral solution, right? Because if it's 10 to the minus 7 molar in H3O plus, it's also 10 to the minus 7 molar in OH minus, and that's neutral. If you take the log of 10 to the minus 7, you get minus 7. If you take the negative base 10 log of 10 to the minus 7, you have 7. So a neutral solution has a pH of 7. As a lot of people already know, but this is where that comes from. Okay. If you have on this next entry, the H3O plus ion concentration is 0.01, that's 10 to the minus 2. Take the log of that, you'd have minus 2. Take the negative log of that, you'd have 2. So the pH of that would be 2. You can see what this is doing. This is just, if you had a perfect power of 10, this is taking the exponent, but the negative of the exponent. So like in this next line is 10 to the minus 1, the pH is 1, okay? That's actually why it's called pH. It comes from power of hydrogen, the power meaning, you know, the exponent on the hydrogen. So if you had, you know, 10 to the minus 6 molar H3O plus, the pH is 6, okay? Some other interesting cases. Suppose you had a 1 molar solution, H3O plus is 1 molar. Well, 10 to the 0 is 1, right? Anything to the 0 power is 1. So a 1 molar solution, that would be 10 to the 0, and the pH would then be 0, okay? So now some people think that pH only runs between 0 and 14. Okay, but actually pH can be negative. Anytime you have an H3O plus ion concentration that's greater than 1 molar, you're going to get a negative pH. Okay, so look at this next example. Now, it's an extremely strong acid, 10 molar. But that would be 10, it does exist, but it's just very strong. 10 to the 1 molar. So you take the log of that, that would be a 1. Take the negative log of it, it's minus 1. Okay, so you can have negative pHs. Those are just very, very strong acids. If you don't have a perfect power of 10, like in this next example, it's just 0.5 molar, well, then you have to get your calculator. You say 5.0 times 10 to the minus 1, take the base 10 log, change the sign, and you get 0.3, okay? And here's another example, 1.5. Now 1.5, that's greater than 1, so it's no surprise you get a minus, you get a negative pH. So I just wanted to point out that you can have negative pHs. Now this next slide is just a figure that I took from a great book by Daniel Harris, Quantitative Chemical Analysis. And it depicts a pH electrode. If you're working in the lab, you actually measure pH with an electronic device. It's a pH electrode, so that's what's depicted here. But more interesting is some of the notations on here. For instance, you notice human blood there between 7 and 8. It's a little bit basic, human blood. Interesting, you know, fish die below a pH of 5, pH 4.5 to 5. Most fish species die. That's in there because there used to be quite a problem. The previous big environmental challenge was acid rain, and some of the streams would become acidic. Vinegar is on here. Most acidic rainfall ever recorded in the United States was, wow, look at that, between pH of 1 and 2. Okay. So there's just some interesting things on here. Thought I'd mention that, and it again reiterates that the pH can be negative or greater than 14. We also define pOH. It's defined in exactly the same way, negative base 10 log of the hydroxide ion concentration. So that's no big deal. And then wanted to say how they're related. How is pH and pOH, how are they related? It comes from this expression that we started with, the equilibrium expression. H3O plus times OH minus is equal to Kw 10 to the minus 14 at 25 degrees C. All right. I'm going to derive a relationship between pH and pOH. Probably I'm going to have to take a log. So let's take a log. Base 10 log of both sides of that. Okay. Now, the log of a product is the sum of the logs, right? Properties of logarithms, so we just expanded that out. And then on the right-hand side of that equation, look, it says log, base 10 log of 10 to the minus 14. Well, that's just minus 14, okay? So we have log of H3O plus log of OH minus equals negative 14. Now, I just want to multiply through by a minus 1. And I have negative log of H3O plus and negative log of OH minus equals 14. But those, of course, are just the definitions of pH and pOH. So we have a relationship that says pOH and plus pH add up to 14. So you can always figure it on that. Anytime you have the pH and you're asked for the pOH, you can figure it out because pH and pOH add up to 14. So now we have a bunch of relationships. We know a relationship between H3O plus and OH minus. We know a relationship between pH and pOH. We know a relationship between pH and H3O plus and between pOH and OH minus. And I'll put all those on. And put all those on a chart here. Okay. Okay. So across the top, H3O plus and OH minus. They're related by the equilibrium expression. Anytime you've got one of them, you can calculate the other. Across the bottom, pH and pOH, they always add up to 14, so anytime you've got one, you can calculate the other. On the left-hand side, if you have H3O plus, you can calculate pH just from the definition of pH. And similarly, if you have, on the right-hand side, if you have OH minus, and you want pOH, you can calculate it from the definition of pOH. Okay. There's only one thing missing, well, two things. If you have pH, how do you get H3O plus? And if you have pOH, how do you get OH minus concentration? That we have to take the definitions and kind of invert them. In other words, we know pH is a negative log of H3O plus. How can I express H3O plus in terms of negative pH? So here's how we can invert that relationship. We start with the pH is equal to the negative log of H3O plus, just the definition. Multiply both sides by minus 1, so you have negative pH is equal to the log of H3O plus. Now I'm going to take each side, raise 10 to the power of each side. So 10 to the minus pH is equal to 10 to the log H3O plus. And then we remember that log and raising 10 to the power are inverse functions. put it this way, 10 to the log x is just x. So this right-hand side is simply H3O plus, and we have the relationship that we need. H3O plus is 10 to the minus pH. And we can put that back in the chart that we were working on a moment ago. Oh, I forgot. There's also the similar relationship between OH and POH. OH is equal to 10 to the minus POH. And you can find that in exactly the same way as we did the derivation over here on the left. Now, let's put it in the chart. There's the one, and there's the other. So now we have this square, 4 different ways of expressing the acidity of a solution. And it's completely redundant. In other words, given any one of these, you can calculate the other 3. All right. So, and this square just sort of summarizes how to do that. But you should be able to get from anywhere on the square to anywhere else on the square. You can go out in different directions. If you want to get from POH to H3O plus, you can go via OH minus or go via pH. And you should reach the same conclusion, but it's just useful to have that summarized.